Hey everyone, welcome to today's explainer. We are literally cracking open the black box today. We've got this incredible technical breakdown and we're going to dissect the anatomy of an AI brain. We want to see exactly how these systems take in the world, how they think, and ultimately how they act. Let's get right into it. But, before we get completely lost in the technical architecture, I want you to consider a fundamental question. What is the actual difference between the calculator app on your phone and the software running, say, a self-driving car? At the end of the day, they're both essentially just lines of code, right? Processing inputs to generate outputs. So where is that line? What actually crosses the line into genuine intelligence? Well, according to our source material, the defining factor here is evolution. Unlike your calculator, which, let's face it, is going to perform the exact same operation the exact same way forever, an intelligent system continuously adapts. It's software that actually evolves. It improves its own logic over time by analyzing raw data and real-world user interactions. It doesn't just execute a command, it actually learns. Okay, so here's our roadmap for the explainer. We'll start with the anatomy of intelligence, then map out the system architecture. After that, we'll look at how the machine actually decides, dive into continuous learning, tackle security, ethics, and uncertainty, and wrap it all up with some real practical cases. All right, part one, the anatomy of intelligence. So, for decades, software development was completely rigid. You had traditional software built on totally static rules. You know the drill. If X happens, do Y. If a bug pops up, a human engineer has to manually go in and write an update. But intelligent systems, they shift this paradigm entirely. We're moving from program to rigid rules to statistical, data-driven intelligence. These systems are specifically designed to handle the messy, totally unpredictable uncertainty of the real world. They learn from the mess rather than just crashing because of it. Moving on to part two, the system architecture. Our source outlines a really specific four-step architectural pipeline. First up is sensing, or data ingestion. This could be physical cameras or maybe just scraping API data. Second is pre-processing, which is where all that raw, messy data gets cleaned up and transformed. Third is the core decision phase, and this is what's powered by the AI models. And finally, the fourth step is action. This is translating that invisible mathematical decision into a tangible output in the real world, like, say, hitting the brakes on a car or sending you a push notification. And this flow is brilliant because you can clearly see the progression. You've got sensors feeding raw data straight into the ingestion and transformation blocks, which then dumps everything into a central storage lake. From there, it feeds right into the machine learning models and business rules, and those models spit out the final action. Honestly, every intelligent system, no matter how complex it seems on the outside, fundamentally relies on this exact plumbing. Which brings us to part three, how the machine decides. When you look at the sheer variety of decision models developers have at their fingertips, it all boils down to trade-offs, right? Like, do you need strict explainability? Go with Boolean rules. Dealing with really noisy data? You might want probabilistic Bayesian networks. Or maybe you're trying to recognize incredibly complex visual patterns, like spotting a pedestrian on a dark street. For that, you need deep neural networks. Though a lot of the time, developers actually use hybrid systems. They combine the raw pattern recognition of deep learning with strict rules just to keep the whole system safe and predictable. And then there's reinforcement learning. Our text pulls this fantastic quote from AWS to describe it. It says, "It trains the software to make decisions to achieve the best results, imitating learning by trial and error." And honestly, the best way to think about this is like training a puppy. You don't hand a puppy a rule book. You put it in an environment, give it a treat when it does something right, and ignore it when it fails. Over time, it learns the absolute optimal behavior just by exploring its environment. It's wild. All right, part four, continuous learning and updating. So AI models don't just magically stay smart. They require very specific updating mechanisms. First, we have batch learning. Think of this like cramming for a massive test completely offline. It's slow, it's incredibly safe, and you just do it periodically. Contrast that with online learning. This updates the model incrementally, in real time, the second new data hits. It makes the system highly agile, but yeah, it's definitely a bit riskier. And then we have transfer learning, which is amazing. You take a massive, already pre-trained model and just refine it for your one specific task. It saves an immense amount of time and computing power. Moving to part five, security, ethics, and uncertainty. Okay, XAI, explainable artificial intelligence. See, as deep neural networks become more and more powerful, they also turn into these opaque black boxes. A lot of the time, we literally don't know exactly why they made a specific choice. So XAI is this entire architectural field dedicated entirely to cracking open that black box, just so humans can actually understand and, more importantly, trust the machine's output. And this isn't just some fun academic exercise. XAI builds essential user trust. It allows for vital system auditing. It even mitigates embedded biases in the training data simply by making the logic totally transparent. Plus, managing statistical uncertainty using things like fuzzy logic, which handles gradients of truth rather than just strict black and white rules, allows these systems to navigate an incredibly noisy real world responsibly. And crucially, this transparency ensures privacy compliance right from the design phase. To really ground this, our source explicitly highlights Law 13.709 from 2018. That's the Brazilian General Data Protection Law, or LGPD, which is very similar to the European GDPR. Look, intelligent systems are ingesting literal mountains of data every day. Privacy by design isn't just a casual nice-to-have suggestion anymore. It is a strict, legally binding requirement for any AI architecture that handles personal information. Finally, Part 6, Real Practical Cases. Let's look at case number 1, the autonomous car. The data inputs here are intense. We're talking 360-degree cameras, LiDAR, radar. The car processes all of this via convolutional neural networks for computer vision. But the key architectural trade-off here is literally life or death. The system has to heavily prioritize maximum security and lightning-fast processing, demanding a latency of under 100 milliseconds. It gladly sacrifices computational cheapness to absolutely guarantee safety. Now contrast that with case number 2, smart urban traffic. Here, a city gathers edge camera and GPS data, but instead of focusing purely on milliseconds, it applies that reinforcement learning we discussed earlier, but at a massive macro scale. The AI agent continuously tests out different traffic light patterns, and it gets rewarded for reducing overall travel times and city congestion. It is quite literally a living system optimizing a whole city grid. And case number 3 takes us right onto the factory floor of the textile industry. You've got high-resolution edge cameras scanning fabrics whizzing by at high speeds. A neural network identifies defects, and then strict business rules instantly trigger an actuator to reject the bad product. The priority here isn't life or death safety, but sheer throughput. It's balancing high precision against false positives to keep that production line moving without a single interruption. When you put all 3 of these architectures side by side, you really see the true genius of system design. The inputs, the models, the updates, they all completely change depending on what the real-world goal is. The car needs instant reaction. The traffic system needs long-term optimization. The factory needs high-volume precision. Intelligence isn't just some one-size-fits-all algorithm. It's a custom-built loop perfectly tailored to its environment. And this continuous cycle finally comes together in a complete feedback loop. You can see how historical data feeds back into the system and how online learning continuously updates the model parameters based on the absolute newest actions. It really proves that an intelligent system is never truly finished. It's a continuous living loop of feedback and action. So, as we wrap up today's explainer, I want to leave you with a thought. We've just seen how these evolving learning systems are completely rewriting the rules for cars, for cities, and for factories. So ask yourself, how will integrating this exact kind of AI architecture transform your own professional world over the next decade? Because the shift from static rules to evolving intelligence, it's already here. Thanks for joining me, and keep learning.